This is the second in a series of videos about buffers. In the last video, we talked about buffer composition and what happens when you disturb a buffer with a strong acid or a base. And in this video, we're going to do an example of a buffer problem involving DNA tables and ice tables to find how much adding a strong acid or base disturbs the pH of the system. Now, there's going to be a lot of math, and it's going to be a long problem, so pull yourself out a couple of fresh sheets of paper. You won't regret putting this on its own page. All right, so here is our problem. How does adding option A, 0.006 moles of HCl, a strong acid, or option B, adding 0.006 moles of sodium hydroxide, a strong base, how does adding a strong acid or a strong base to this volume of a buffer that has this concentration of weak acid and this concentration of weak base change the pH? Here's our Ka value. So our buffer is going to be this part, weak acid, acetic acid, and it's going to be this part, which is the weak base. Remember, a buffer is relatively equal amounts of a conjugate acid-base pair mixed together. And this is going to be the Ka for that reaction. So we want to find out what the change in pH is for this buffer. So the first thing we need to do is verify that it is a buffer. It says so in the problem, but we want to make sure. So remember that a buffer, the ratio of the two pieces, the concentration of conjugate base and the concentration of conjugate acid, needs to be between 10 within the buffer region for the buffer to work. So if we check that fraction, the weak base is going to be sodium acetate, 0.56, and our weak acid is going to be acetic acid, concentration 0.25, and that number is 2.24. And 2.24 is greater than 1/10, and it's less than 10. Check. This is in fact a buffer. So now we can look at how to find the answer to the problem. So we need to find the pH change. So not just the pH change. So let's write that down so we don't forget. We need to find pH change. And to find the change in anything with a delta, we need to have the initial value and the final value. So we're actually going to have two final values, one for the strong acid and one for the strong base in part B. But we need to take each of those minus the initial value. So let's do the initial first. The initial is when we have the buffer by itself. We haven't disturbed it with any strong piece. So initially, we're just going to have the conjugate acid-base pair in the solution alone. So this should look like a common ion effect problem, even though I promise never to mention it again. When you just have a weak acid and a weak base, they are both part of the same reaction. And so we'll use an ice table. Use ice tables to find the pH of weak systems. And for ice tables, we use the ion dissociation reaction. Since we have an acid and a base, we could choose the acid dissociation reaction, or we could choose the base dissociation reaction. But looking ahead, I know I need to find pH, and pH is easiest to find from the acid reaction. So I'm going to pick that one. You can absolutely pick the other one if your heart tells you to do that. Okay, so this is my acid ionization reaction. Weak acid plus water. And we can go ahead and plug in any initial values. So we've been given initial weak acid concentration, 0.25. We ignore water, We've been given initial weak base concentration of 0.56, and we start with approximately 0 of hydronium. We figure out which direction the shift is. We note that there is 0 over here on the product side, so we're going to be shifting to the right. Subtract reactants, add products, and this is a weak acid-base reaction. So that shift amount is unknown. It's going to be some small number x. And we add down to the bottom to our equilibrium row. There we are. Step 1 is the shift. Step 2 is the ice table. Step 3, use the K expression and the E line to solve for x. All right, so products over reactants, 0.56 plus x times x divided by 0.25 minus x. And our Ka was given, or we might even have it memorized by now because we use acetic acid so much, 1.8 times 10 to the negative 5. And noting how much smaller 0.25 is than 1.8 times 10 to the negative 5, I'm going to use my assumption. The superhero uses assumption. It may or may not be effective. We'll see. So we're going to assume x is much smaller than 0.25. So we can leave out this x, and we can leave out that x. So that leaves us with 0.56 times x over 0.25 equals the Ka. And we can solve for x, and you should get 8 times 10 to the negative 6th molar. And we never walk away without checking our assumption. So we'll check it. We'll take x divided by the number it was being subtracted from, HA initial, converted to a percent, and that should give us a very small number, 0.003%. And we said we would be happy with less than 5% error, so we are happy with that. Hero uses assumption. Assumption is very effective. Okay, and we are trying to find pH. Got to focus on the goal. So step 4, answer the question. Question wants pH. pH equals negative log of hydronium concentration. And our hydronium concentration at equilibrium was x, so we can just stick this number straight into the formula. pH equals 5.09. And we'll put a little subscript I since this is our initial condition. There we are. Finished with our initial, not even the fun part of the A or B. So this is initial, so now we're going to turn the page because we definitely need more space, and we're going to look at what happens to the buffer when we add a strong acid. Okay, so we add a strong acid. Remember from our picture before, when we're fighting the supervillain strong acid, which is H3O+, superhero uses neutralize with weak base. And if we're going to be doing a neutralization, we need to use a DNA table, and DNA tables are in molarity. So we need to convert our number of moles to molarity, or rather convert our molarity into moles, sorry. So we had 0.250 moles per liter of HA, and we had 0.560 moles per liter of A minus. And let's go back and check. The last one, we were given the volume, it was 300 milliliters. So we'll multiply our molarity times the volume to get to the moles. Liters cancel, liters cancel. Calculator says 0.075 moles of HA initially, and 0.168 moles of A minus initially. All right, we've got our moles. We are ready to start the DNA table. DNA table is going to be in moles, and our equation is going to be the neutralization reaction. So we're going to take our weak base, use it to neutralize our strong acid. We'll write it as H3O plus because that's effectively what it is. It goes all the way to completion, and it forms the conjugate acid and water. Looks like I'm being lazy and not including the phase information. We really should. Panic, go back and add it. Aqueous. Okay, we're good now. So this is going to be a table of moles. So we had 0.168 moles of conjugate base. We have 0.075 moles of our conjugate acid. We don't include water. And then D is for disturb. So we're going to disturb it with some amount of H3O plus. It was 0.0060 moles that was added. N is for neutralize. We're going to neutralize our strong acid by subtracting it all the way out to 0 and shifting the other amounts accordingly. And then we'll do a little bit of math here to add those together. Okay. So we neutralize that strong piece with our DNA table. So now all we have left is a weak base and a weak acid. So it looks a lot like when we did the initial situation on the last page. And we know whenever we have a solution of weak acid and weak base, we need to do an ICE table to find the pH. And ICE tables are in units of molarity. So now we need to go back to molarity using that volume. So we had 0.081 moles of HA, and we have 0.162 moles of A minus from the table. And we'll divide each of those by the total volume, 0.3 liters. Hopefully I left enough space. Calculator says 0.270 molarity of HA after the neutralization, and 0.540 molarity of A minus after the neutralization. And let me just point out that not only do I have a unit moles per liter for this number, I also have a compound label and a timing label for what part of the problem we're in. But I'm doing that to make sure I keep track of what this number means, because we are doing an awful lot of calculations in this problem and we're not done. So we don't want to get lost in the middle of a problem. So we want to make sure we adequately label what exactly is going on. All right, now to the traditional ICE table. ICE tables use ionization, and again, we have an acid and a base, so we can choose either the acid or base ionization reaction, but it's easier to get the pH from the acid reaction. So I'm going to pick that one. So HA plus liquid water sometimes goes to, or rather partially goes to, conjugate base and hydronium. You are going to be seeing these tables in your sleep. Okay, so let's put in our initial numbers in molarity. So here's our initial molarity for the weak acid. And here's our initial molarity for our weak base. We ignore water. And now that we've done the neutralization, we don't have any of the strong piece left. So this number is approximately 0. So this is a part where students often get hung up. So we shouldn't have any of the strong acid in our ice table because we neutralized it in our DNA table. Okay, so now we look at our shift direction. Step 1, there's a 0 on the product side. So we're going to shift towards the right, subtract the reactants, add the products. And this is a weak acid-base system, which means we are going to subtract some small unknown amount, x. 1x for each of them, and we'll add down. All right, step 2, ice table. Step 3, solve for x using the equilibrium line. In our Ka expression, products over reactants, 0.540 plus x times x over 0.270 minus x. And our K value was on the previous page, 1.8 times 10 to the negative 5th. And I can see that this concentration is much larger than this Ka value. So I'm going to use my assumption. Assume x is way smaller than 0.27. So I can ignore this number and ignore this number. So that simplifies to 0.540 times x over 0.270 equals the Ka. We can solve that. Calculator says 9.0 times 10 to the negative 6th molar. And that x looks pretty small to me. But we promised that every time we used our assumption, we would check whether it was legal or not. So we check our x over the number we subtracted it from, HA initial, multiply by 100%. And calculator says 0.003% error again, which is less than our comfort limit of 5%. Highly effective assumption. Okay, step 3 complete. Step 4 is to answer the question. Way back wherever we had the question, our goal was to find the pH, which is the negative log of hydronium. And hydronium was here, it was X. So we can just plug this number straight in. You're almost going off the page here. pH equals 5.04. And we'll call this pH acid just so we remember which one this is. Okay. And the original question, way back here, wanted to know the change in pH. So we need to take final minus initial to finish answering that question. So the acidic pH is 5.04. On the previous page, our initial pH was 5.09. So our change in pH equals negative 0.05. Let's fix that. Okay, negative 0.05. So as we expected when we added an acid, the pH did go down, but because it was a buffer, it only went down a little teeny bit, just a little bit. Okay, are you ready to find what happens when we add strong base? I'm sorry, I know this is a very long video, but it wouldn't have made sense if it was separated into pieces. So we continue to push forward, strong base. All right. So this should look very similar to the last one, except completely the opposite. So in this case, we're adding a strong base. And remember that when we're fighting supervillain hydroxide, the hero uses neutralize with weak acid. And if we're doing a neutralization, neutralization needs a DNA table. DNA tables need to be in moles. Fortunately, we did all that math converting to moles on the last video. So we're just going to go ahead and use those numbers so we don't have to do them again. There's got to be some benefit to doing the same question over and over again. Okay, so the DNA table needs a neutralization reaction. We're using our weak acid to neutralize. We are going to neutralize strong base, which provides hydroxide. We are going to totally and completely neutralize to conjugate base and water. All right, we are going to cheat because we already found those numbers on the previous video and everything is exactly the same. So for our weak acid, we have 0.075 moles. 0.075. For our weak base, we have 0.168 moles. And we added 0.006 moles of strong base. And we don't include water. Okay, so we have our happy little buffer. We disturb it, D, with a strong base. So we're going to neutralize that strong base. We're going to use it all up until it goes to 0. So we're going to subtract it from the reactants. We're going to add it to the products. And then we're going to do a little bit of math to find our values after the neutralization. There we are. Strong base was neutralized to 0. And so now that we've done our neutralization, we are left with weak acid and weak base. So to find the pH, we need to do an ice table. An ice table needs to happen in molarity. So we still have to do this part because now our numbers are different. So we have 0.069 moles of HA. We have 0.174 moles of A minus. And our volume, remember, was 300 milliliters. Do a quick conversion back. Calculator says 0.23 moles per liter of HA after the neutralization. And 0.58 moles per liter of conjugate base after the neutralization. Got our molarities ready to go. So we set up our ice table, and ice tables use ionization reactions for either the acid or the base. I like the acid one better. Weak acid plus water goes to conjugate base plus hydronium. I hope we're almost done. My hand is starting to get tired of writing all of this. Okay, so from HA, we started out with 0.23 molarity initially. We don't include water. Our conjugate base, we had 0.58 molarity. And we have approximately 0 hydronium. Remember, we used up all of it in the previous one. It doesn't match the last table because I decided to go with the weak acid table instead of the weak base. But in the weak base table, there would have been a 0 as well. The most important thing is that by the time you reach your ice table, you should hopefully not have any of the strong acid or base left. When we have 0, step 1, we're going to shift towards the right, lose reactants, add products, weak acid, meaning we only partially dissociate, so we subtract small number x, add down, step 3, Use the equilibrium line and plug it into our Ka, products over reactants, 0.58 plus X times X over 0.23 minus X equals our Ka for acetic acid, 1.8 times 10 to the negative fifth. This number is small. This number is super small. So we're going to pull out our assumption and assume X is much smaller than 0.23. So we can ignore this number and ignore this number. Simplify, 0.58 times X over 0.23 equals the Ka. Solve. Calculator says 7.1 times 10 to the negative sixth molarity. And we'll check our assumption. Make sure X over the number it was subtracted from has a less than 5% error. Calculator says 0.003% error, which is less than 5. So our assumption is okay. Step 4, answer the question. Find the pH. pH is negative log of hydronium. Hydronium is X according to my equilibrium table, so I can stick this number straight in. And we should get 5.14, and we'll label that as pH with base. And finally, the question wanted the change in pH, not just the pH itself. So we'll compare that to our initial pH of 5.09. And we see that our change in pH, 5.14 minus 5.09, is plus 0.05. So as expected, when we added a base, the pH went up just a little bit, but because it was a buffer, it didn't change very much. So the buffer has successfully resisted change in pH with small additions of strong acid and strong base. In the next video, we will talk about a new trick, the Henderson-Hasselbalch equation, which will save us some serious amounts of work in doing these buffer problems.